Lab 2, Lines of Charge.
One of our main ideas, the electric field, is a region of space around an electrically charged particle or object in which an electric charge would feel a force. A point charge is what it sounds, is a charge located at a specific point. Another main idea in this lab is Newton's second law, which states the acceleration of a particle is proportional to the sum of the forces acting on it in the direction of the resulting force. Another component of this lab, a very important one, is superposition. The electric field contributed is unaffected by the charge of another particle in proximity, and most importantly, it states the net electric field at a place is the sum of the electric fields of the charged particles in proximity. Matter cannot block electric fields. And Coulomb's law, which is the formula we use, speaks to the quantity of the force between two charged particles, and it is embodied by the equation F equals 1 over 4 pi epsilon naught times charge A times charge B all over the magnitude of R squared times R hat, or the unit vector.
In Newton's second law, how it applies to our lab is when we have our two tapes reacting with each other and moving the other tape, they at some point are in equilibrium, meaning they do not move, which means that the net force on them has to be equal, which we know means that the electric field force must cancel out with the gravitational force. In order to do this, as we said, the net component of the y force must be 0.
Lab 1 is very closely related to this lab, Lab 2. So we know what we're talking about, I'll give a quick overview of Lab 1. So we talked about charge interactions, how like charges repel and how opposites attract. Tape interactions, how we had induced dipoles because a dipole occurs with a neutral charge and charge. So when we had a neutral object like our head come close to a tape, charge object, there was an attraction. And how in the previous law we treated our tapes like point charges where we had one point representing the entire charge of the tape. So we used that and calculated the charge of the tape as a point charge, the number of electrons, the number of atoms, and the ratio of electrons to atoms.
We made some assumptions in this lab. One of the assumptions it asked if we did is, did we ignore air resistance? Well, it's kind of a trick question because since these tapes are at equilibrium, air resistance isn't even a determining factor. So it's not, we can't say exactly that we ignored it, but we can say that we didn't even take it into account because it isn't relevant here. We did assume that they're the same amount of charge, and since we're using a line charge in this lab instead of a point charge, we're taking into account how we have 10 lined point charges representing an entire piece of tape, which we know is not one-dimensional, but here we just take it into account so we get a more accurate determination of the charge of the tape in layperson's terms. So at the beginning, we have our input values such as our calculated charge of last lab, mass of our tape, the number of point charges we split into, which in this case we decided is 10. Next, we create our electric field using the variables which play a role. Then we create our line charge, like object, where we use the variables that play a role there, and then we choose how to scale our vectors. But the most important part of this code is how we have a double for loop that iterates through each point charge, finding the electric field relative at that point. Then we can eventually use the superposition principle, which states the net electric field at a location in space is the vector sum of the individual electric fields contributed by all charged particles located elsewhere. And when we say elsewhere here, we mean along our piece of tape. So then we can use our relative point charges nearby to get a more accurate calculation of what the charge of our tape is.
Because our tapes will be at equilibrium, we know they're not moving, so for them to not move, we know their forces have to be equal and opposite, and for that, we can either go through different values of Q to show how this happens. So we first start with our original value of Q, which is 5.647 times 10 to the negative 9, and we know that that one isn't 100% accurate because when we calculate the magnitude of the electric force, the magnitude of the gravitational force, they're different. So we know we have to change that. So that's when we go up to the next.
Now we chose a charge of 6.0467 times 10 to the negative 9 coulombs, and that got us a magnitude of electric field at 1.55499 times 10 to the negative 3. Now that's even closer. So we know.
So we go to a value of 6.44653 times 10 to the negative 9 as our charge. We get closer, but we're not quite there, so we go up again.
This time we choose a charge of 6.8463 times 10 to the negative 9, and this time we get our magnitude of our electric force and the magnitude of our gravitational force to be equivalent to each other. And so we know that this has to be the accurate charge of Q because of Newton's second law, and because those tapes aren't moving, they're in equilibrium, they have a net force of 0, meaning that those two forces must be equal to each other, ergo, this is the correct charge of tape.
If we model each tape like a single point, it'd be less accurate. A tape divided into many different parts is more accurate because due to superposition, we know that the net electric field at a location in space is the vector sum of the individual electric fields contributed by all charged particles located elsewhere. And this elsewhere meaning the reference is referencing the point charges the tape is separated into, and we know a line charge is going to be more accurate because of that. So these different models are different because a point charge is one representative charge for an entire piece of tape, whereas a line charge, we chose 10 in this case, is 10 point charges representing representing the tape. So it's going to be more
space around an electric charge particle or object in which an electric charge would feel a force. We know the opposites attract and likes repel, and how dipoles are created by a neutral and charged object like we saw in lab 1. We know how in Newton's second law that the electric force and the gravitational force would balance each other out because they're in equilibrium because those tapes were not moving. And finally, we look at what assumptions we made throughout the lab, such as ignoring air resistance in calculations, which isn't exactly what we did, because since the system's in equilibrium, air resistance isn't even a determining factor, so we didn't even think about air resistance. It wasn't even relevant here at all. But we did not treat our tapes like point charges like we did in the previous lab. We had a more representative line instead, and then we took each of our tapes as basically one-dimensional, using this line of tapes to represent an entire piece of tape. And most importantly, we used our superposition principle, which states the net electric field at a location in space is the vector sum of the individual electric fields contributed by our charged particles located elsewhere, which is how we could do our lab by iterating through double for loops to get a more accurate value for our charged piece of tape. Thank you.